Okay, so this is going to be kind of a long explanation, but I think it's important to know and understand the entire thing. So we have right here what we know as the neuromuscular connection here, neuromuscular junction. So neuromuscular junction right here. So we have a presynaptic gap, presynaptic neuron, the synaptic gap, and the postsynaptic neuron. So the brain is over here. You have the, medulla, all that jazz right there. So that's the brain. When the brain sends an electrical signal, comes down the neurons, and what it does is activates, it causes an action potential. So what's an action potential? Well, we have to remember that the inside of every cell in our body is negative. It's predominantly negative, okay? So when we start an action potential, the action potential is going to cause the opening of sodium channels. So once the sodium goes in, or sodium rushes in, more sodium rushes in, the influx of these positive charges of the sodium are going to cause the inside to turn positive. Once the neuron reaches at a threshold in positive charge, let's say once it gets to 25 from negative 90, it opens calcium gated ion or calcium ion gates, voltage gated calcium ions. That's what it is. So calcium rushes in. And what's the purpose of that calcium rushing in? Well, the calcium rushes in to make it even more positive. Once that happens, right here we have some vacuoles, and these vacuoles have a bunch of neurotransmitters there. So once the inside of the cell turns positive, these vacuoles come to the membrane, merge with the membrane, and release all these neurotransmitters. These neurotransmitters are going to bind with all these receptors right here, and they will cause a reaction. For example, let's talk about epi, being the most important neurotransmitter of the sympathetic system. So if I want to breathe, my brain will send a signal to breathe. We'll have an action potential, sodium will flow in, calcium will flow in, and then we have this release of neurotransmitters. Okay, so that will lead to an increased heart rate, an increased respiratory rate, an increased happiness. Essentially, fight or flight activation, right, with epi. Well, this is where another cell comes in play. Right here, there's another type of cell, and when this cell is in charge of releasing a hormone that keeps epi in check. So it doesn't allow epi to be in a lot of presence here, because if we have a lot of epi right here, we'll have a very increased heart rate, a very increased respiration, and a very increased, like mania kind of thing. Okay. And sorry, I'm gonna try to be concise here. So anyway, this cell releases this compound called gamma aminobutyric acid. Gamma aminobutyric acid, GABA for short. What is the purpose of GABA? It's very complex, man. I don't want to confuse you or lose you, so I'm going to simplify GABA. So what GABA does, GABA opens some channels right here that allow the influx of chloride. So now let's think about this. Chloride is a negative ion, it's an anion. The influx of chloride into the cell will decrease the voltage or make it more positive, more negative. If the inside is more negative, we won't be able to initiate another action potential in the adjacent cell. So GABA stops epinephrine in an essence. Does that make sense? Every time we activate GABA, every time we release GABA, we have influx of chloride. The inside is going to be more negative. Therefore, we don't have an increased respiratory rate or heart rate or smiles. Now, why did I go on all this tangent? It is believed that Keppra stops the disintegration of this vacuole. Therefore, the vacuole will never release the neurotransmitter into the cell. So why is that good? Well, let's say that we have another cell right here. And that cell, let's say that the brain right here is going crazy and is sending a shit ton of signals. This hyperstimulation from the brain will lead to what? Convulsions, seizures, right? All this will lead to seizures. So what we need to do is to stop these seizures, and we stop the seizures by two ways. So I'm gonna write it right here, seizures. And we stop in two main ways. Main number one, we're going to stop the actual potential, or stop the release. Stop the release of the neurotransmitter. So let's talk about the stop the action potential, which is something that the benzo will do. So benzos, right here, benzos. We have three flavors, you know, lorazepam, midazolam, all that jazz. So we have Ativan, Versed, and I'm missing one for some reason, diazepam, Valium. Okay, all these benzos, what they are gonna do, benzos potentiate GABA. Benzos potentiate GABA, meaning they will increase the influx of chloride. By increasing the influx of chloride, we stop all this action potential. By stopping the action potential, we have a change in mental status. We are not breathing, and we can become bradycardic. Therefore, our BP will drop. Those are benzos. Okay, so benzos essentially work right here in the postsynaptic neuron by means of GABA. Keppra stops the release of the neurotransmitter right here. Now, another medication that is good to talk about right now is Dilantin. Dilantin is a sodium channel blocker. So what it does is it inhibits the sodium from going in. Therefore, we stop the action potential at its roots. So the cell never becomes positive. Therefore, we will never have this release. Therefore, nothing will be stimulated in the adjacent cell. Therefore, none of this. Does that make sense? It's important to know that as a sodium channel, sodium channel blocker, this is also used as a class 1 antiarrhythmic. Follow the same principle, along with procainamide. But anyway, super complex. Hopefully this loads, and hopefully you can see it, brother, and let me know what you think. Talk to you later. Bye.